Hey Honors Physics, this is Mr. Hausman. We're going to be looking today at two-dimensional collisions. So far, every type of collision or interaction we've had in which there was momentum conservation was in one dimension. One dimension means that the objects, right, are moving in a single line. Maybe object A has momentum and it hits object B. B is at rest. And maybe B moves backwards, right, in the same direction. See how everything is on the x-axis. And that's all great, and most of us have mastered that. So it's now time to see if we can conserve momentum in two dimensions. We're going to be having to keep track of the momentum in the x direction as well as momentum in the y direction. We're going to see some examples of this, but it's quite challenging to actually measure this in real life because of lots of angles and separate velocities. So let's imagine you're playing a game of pool. Maybe 8-ball on your iPhone game, or maybe in real life. So here comes the cue ball, and it's going to strike maybe the 8-ball. And it looks like it's going to go in a straight line. But what we have to imagine is that this vector is maybe slightly off axis. That doesn't mean that it has a y component, but what we're going to say is that it hits this ball maybe not in its center. And if you've ever played a pool, you know that that's how you get a ball to basically go in a different direction. Instead of hitting it from the center to center, you hit it off center. Okay, now mass 1, the cue ball, has to have a velocity, right? So we know that that's going to be called v1. And mass 2, we're going to say is at rest. In the game of pool, it's, you wait until the balls come to rest if you don't know that, and the result is then the next person takes their shot. But mass 2 has a velocity of 0. So we already know that that means that mass 2 is not going to be contributing any momentum to this initial situation. Now, after the collision, we notice that mass 1 goes off on an angle theta, and it has a new velocity. And remember, we use the prime notation to show that it is, actually, let me use the same colors, right? The prime means final velocity, or after the collision. Mass 2, on the other hand, which way does it go? Well, it goes off on an angle phi, or phi if you prefer, and that's not necessarily the same angle as theta. It could be a different angle. It really depends on how you hit it. So here it goes, and now it has its own final velocity. So I hope it's not that far from your memory that we've talked extensively about how velocities on angles, right, angled velocities, can be resolved into their components. So let's imagine how we would picture that momentum. Well, mass 1 goes into the first quadrant, so some of its momentum is in the x direction. So we could call that m1, v1 prime, and we're going to add an x to that, v1x. But it also has a y component. So it would be m1 times v1 prime, but it's the y component. Okay? A little tricky, and we hopefully remember that to find those two sides, we would need to introduce sine of the angle to get the y component, because it's opposite, and then we would have to introduce cosine of the angle theta to actually resolve the velocity into its components. Now, masses are not vectors, of course, so we're really just resolving the velocity. Okay, what about mass 2? Mass 2, on the other hand, has its own x component, and it would be very confusing to draw it up here on the original picture because they'd actually be on top of each other. They'd be in the same axis. So by drawing them a little bit separate like this, we now get m2 v2 prime x. Let me zoom in on that so you can see it a little better. That's not going to work today, so we'll just keep going. I'll remember to zoom in next time. And here we have m2 v2 prime, but in the y direction. Now, hopefully you notice that two y components, the red one for the M1 and the blue one for mass 2, they're in opposite directions, right? So one of these is going to have to be positive. The red one's going to be positive. The blue one's going to be negative. I'm referring to, of course, these two guys. On the other hand, the x momentums for both of them remain positive, right? They both keep moving in the forward direction. Okay, so if you can identify or see the momentum in each object, now it's time to come up with an equation. Because we stated earlier, and it may not have hit home, that basically we can now make an equation, let's use just blue, for momentum, that's not blue, for momentum in the x direction. So what we're saying here is that momentum is conserved in the x direction. And to come up with a mathematical statement for that, we look back at the before conditions. Let's look up here. And we notice that mass 1 has all of its momentum in the x direction. So it's mass 1 and its initial velocity. You don't have to call it v1x. It's drawn or it's shown to be in the x direction. Okay? Then let's see how the momentum's in the x direction. But there's two of them. We need to add both together. So it's m1 v1 cosine theta, m2 v2 prime cosine phi. And remember, cosine always is used for finding the adjacent side, and both of these are adjacent to their respective angles. So that equation will come with time. You don't really have to memorize it, but it will matter that you can kind of refer back to this page. Now, in the y direction, something interesting happens. Look back at the top. Mass 1 has all the momentum and mass 2 has none. This is before the collision. And in fact, mass 1 is not moving in the x direction whatsoever. It starts off with 0 momentum. You could technically put in m times 0, m1 times 0, but it's not moving in the y direction at all. Afterwards, how many different y momentums do we have to add in? Well, we've got m1 v1 prime of sine theta, and we also have m2 v2 y, of course, and I didn't put it in over here, but this would, of course, be sine of phi. Now, theta has a horizontal cross, and phi or phi has kind of a vertical or like mostly diagonal cross through it. I'm not quite a Greek letter expert, but that'll get the job done to differentiate the two. Okay, now, what the heck's going on? Why is there a subtraction when it really should be an addition? Well, you can use either addition or subtraction, but you have to be very careful. So if you use the phi angle, that is, quote unquote, a small angle, maybe a negative angle below the east direction, you'll notice that it will not come out to be a negative y component. So what we're doing is we're inserting a y component that's negative. Let me say that again. We're subtracting because the y component, component vector of momentum for mass 2 is negative. It's in the fourth quadrant. If you don't want to remember that there's a weird difference here, it's not weird, it's just why it's explained, but if you don't want to have to remember a different formula, if you want to make it truly a sum, I'll give you a hint. You could take your phi angle, which is a small angle in the fourth quadrant, right up here, and you could find the theta angle, the one that represents this angle, but remember the skill we learned? So if you want to convert this, and I know it's confusing because then it'll be like, wait, there's two theta angles. But if you do this as 360 minus phi, then guess what? It will automatically give you a negative component. And then you don't have to have two negatives, right? It would be plus a negative component. It really depends on your way of thinking and which you prefer. A lot of you have made this a habit this year of finding the theta angle in each quadrant. So that's the theory, but in practice, it's a little bit tricky. So where have we seen two-dimensional collisions? Well, we've seen two-dimensional collisions in silly examples like this. I don't know if you've ever seen this activity at a game, at a party. Now, these do look like they're one-dimensional collisions, but if two people don't hit exactly on axis, right? I just kind of found this comical. It looks like the person's going to be injured, but hopefully the bubble protects them during the collision. I guess that's maybe not truly a two-dimensional collision. Okay, let's stop that guy. Or maybe it has to keep playing. There we go, stop it. Now, what's going on with this baseball? I could not find quick and easy pictures of a pool ball hitting another pool ball in a game situation. So I decided to make it kind of ridiculous. And let's simply say that we have some kind of ball and we are throwing it at, and I tried to figure out, we shouldn't really be throwing it at animals, but let's throw it at this big bear, okay? He's not going to feel it. She's not going to feel it. It's still ridiculous, okay? So here we have mass 1, and it's got a velocity 1, and this bear is at rest, right? So if you start to kind of picture what would happen here, right, this ball is going to come moving into the bear, hit him in the butt, and the bear is going to, if you don't hit it straight forward, right, causing the bear to go this way, what might happen if you hit it kind of off angle like this is the bear goes careening off in the positive, kind of to a kind of the northeast corner. But this ball ends up going off in this direction. So if we look at the vectors, right, that we started with, we had an initial velocity, then we had the bear moving off in this way, right, with momentum, m2, v2 prime, and the ball itself, right, moving off, and that's m1, v1 prime. So if you ever have to draw your own, my strong suggestion, if you have this kind of collision, is that you draw in your components, and I know we did this on the previous page, show the components of each momentum vector. Let's do this in another color, just like we did on the previous page. And here we have the y component, and again you'll see that they have both a positive x, right? Positive x here, but then they have negative y, positive y, and a negative y component. That's not the best animation, but I really did struggle to find really clear examples. But it's a very common situation in the game of pool. And I actually found a great video on learning to play pool. And all you have to do is understand collisions in 2 dimensions, and you can be amazing at pool. Sure, there's trick shots and spin and things like that, but it's really all about being able to see your angles. So that's a kind of a fun video for another day. Simple problem. These two. This is page number 16. Now this one is more like the initial setup. These are, I guess, just a slightly different variety. Mass 1 has X momentum, mass 2 has no momentum. This is before they collide. And then after they collide is on the right side of this coordinate plane. Here's the angle and the velocity. So now we actually have more data, and you might find these just different. Some people who like plugging in concrete numbers might find them a little bit easier. But here, I'll give you a hint. You have 2 unknowns, but they're in the same, they're in one of the masses, right? Find the magnitude and direction of the second ball. And you'll be able to do that by solving your X and Y separately and come up with that. I, again, will be posting a separate video for those guys. Good luck. And certainly, I understand this is going to be not a one-day lesson. We'll be having some follow-up on this. To page number 19. And we're going to do something a little different. These I have found students get a little bit more easily at the beginning. And then we're going to go do harder ones. So I guess the packet's a little out of order. Now these collisions are pretty comical. They're not too real. I guess one's a car collision. One's 2 eagles. What? Well, I don't know why. They're going for the same prey. They have a mid-air collision. Let's just go with it. So we have one bird of prey, right, M1. It's 4.3 kilograms, and we have M2. Now, these guys are not in a straight line to each other. M1 is not hitting M2 straight on. These two are coming in, and they both have momentum, right? So we have a V1, and we have a V2. And you could put an initial next to that. But in this case, they both are contributing momentum. Now, when they collide midair, I don't know, their talons intertwine, they tangle together, they're going for the same prey, and I don't know how this happens, but it's a possible scenario, and we'll go with it. What they do is they move together. And we haven't seen that example, but again, trust me, you'll find it much easier. But what happens now is that the two masses combine, and they end up with a V prime of their own, but it's not V1 prime, it's not V2 prime, it's a combined one. And you may say that seems totally different than what you just showed us. But in reality, we'll see that it's really easy when the two masses come in with their own momentums. So let's separate the two equations. Let's do momentum in the x direction. Well, we know that there's only one mass that contributes momentum in the x direction, right? The sum of the momentum in the x initial has to be equal to the sum of the momentum in the x final. But let's notice that the bird, number one, has, right, all of the initial momentum. So M1 times V1. Now, after the collision, though, something kind of weird happens, is that their momentum finals are combining. So notice what I'm referring to is that this velocity vector is also the same direction as the momentum vector. So this bird is contributing all of it. So this becomes, right, this vector of momentum has to be equal to the momentum after. So this picture is a little different. Here's the before the collision, and then after the collision is kind of on the other side of the picture. So what we know in the x direction is that it is M1 plus M2, V prime, but it's cosine of the angle theta. Now, we don't know what that angle is. We're about to put it in. The actual unknowns are going to be V prime and the angle theta, and we'll have two of them, and we'll see how we're going to work that. This is pretty challenging, but I think we're up to it. Now let's go down to the y direction. Okay? And we can't plug anything in yet. We're just going to set up both. Momentum in the y direction, initial, has to equal the total of the y momentum, final. But notice again, the lower bird, the bird that's coming in from the bottom, is the only momentum that's in the y direction. So that's M2, V2. But where does that momentum go? Well, it becomes the y component afterwards. Because if one object is contributing all the y momentum before, that has to be the same as the y component. So that's M1 plus M2 V prime, but this one is sine of theta. Okay, now can any of this be substituted? Can we simplify any of this? Of course we can. We have 4.3 kilograms times 7.8 meters per second. We know that the combined mass of 4.3 and 5.6 is going to be 9.9. And we've got V prime, and we've got cosine theta. M2 is, of course, 5.6. It's moving at 10.2 meters per second. Their combined mass is still 9.9. V prime sine theta. Okay, can these equations be solved the way they are? And most of us know that you can't solve either equation because you have two unknowns in both of them. But do you notice a fun connection? They both have the same unknowns. They both have theta, and they both have V prime. So, as promised, this is a challenging problem, but most people take to it pretty easily. 33.54, just to simplify the left, equals 9.9 V prime cosine theta. 5.6 times 10.2, 57.12 equals 9.9 V1 sine theta. So those of you who might have, everyone's in Algebra 2 or pre-calculus. I think one or more of you might be in calculus. But in the context of this problem, how do you go about solving two equations that have basically two unknowns, v prime and theta? And you might know that there's substitution is one way of doing it. But these are pretty complex formulas, and you might not want to substitute. I see this as a chance to do systems of equations. And what I mean by this is we're going to call this equation A, and we're going to call this one equation B. And one of the rules of systems of equations is that you can take two equations, and if it helps simplify, you can divide them. We're going to divide A by B. We're going to take 57.12 equals 9.9 VI sine theta, and we're going to divide it by 33.54 equals 9.9 V1 cosine theta. And you're like, what does that accomplish? Well, I hope you notice that it cancels out the masses, the combined masses. It cancels out the V prime, and of course, when you simplify the constants on the left side, 57.12 divided by 33.54, you get 1.70, and then you get sine over cosine of the same angle. And a couple of times this year, we've noticed that matters. That's called a trig identity. It's a very basic one. And the ratio of sine over cosine is tangent of that angle. So you can solve for the angle by just taking inverse tan to the negative 1 of 1.70. Make sure you're in degrees. I got to check that myself. Nice. And you get 59.5 degrees. Now, how do you go about solving V prime? You can actually take that 59 and plug it into either one of your individual equations, and you will end up with V prime. And V prime ends up being 57.12 divided by 9.9 divided by sine of 59.5. I'm using the bottom equation, equation A, and I'm simplifying by dividing by 9.9. I'm dividing by sine of 59.5, and I get a V, this is a V prime. It's not a V initial, it's a V prime. I must have made a mistake there. And that's equal to 6.7 meters per second. So maybe not easier, but certainly what I like and what most students find about it is that they can clearly identify that the one mass contributes all of the x momentum. The other mass, the one that's coming here from the bottom of the page, contributes all of the y momentum. You separated, remember what we did? We separated our equations of all of our x momentum before and after. We showed our components to help our brain stay clear that our momentum final is, of course, a combined mass times a combined velocity, right? The masses they're acting as one. And that is a great kind of setup for this problem. The bottom of this page is almost identical, and so I'm going to challenge you to do that one. I will be posting the answer to that one a little later today. Okay, if you are a remote student, which you should be watching this if that's the case, I'm going to then challenge you